Last video on the applications of integration, and what I'm going to look at today is very fun: volumes of solids of revolution. In other words, what's the volume of something, a solid that's been created by just rotating something around? And I'll sort of explain what I mean. So if you have some function, let's just say something like that. Sorry, my functions always look the same. That's alright. Between A and B. So you take this. So what you do is you take this area here of this function f of x. And if you can imagine, it's hard on this thing, but if you take that and rotate that around the x-axis, so that's the x-axis, if you can imagine that being rotated around the x-axis, then you make this three-dimensional shape. And I'll try to sort of draw what it will look like. It will sort of look like this, and it will sort of go in and sort of go out like that. It's pretty bad, but so what you can see is that is being rotated. In other words, this is your function here. That's sort of your function, and this is the x-axis. So if that's the green is the x-axis there. The green axis will be sort of straight. Well, that's terrible. Will be straight down the center of that. It's even worse. Maybe from the bottom might help. Not that much better. So what's happened is that red area there, that's that sort of shaded in part like that, and it's been rotated around. And so you end up with this three-dimensional shape. The volume of one of these shapes, if you figure it out, and I've showed this in class, but it's pi out the front from A to B of f of x squared dx. And this is equivalent to the sum of all the pi r squareds. But that's the formula. So if you've got a function of x, if it's rotated around the x-axis, then you'll get that. And in particular, these points here, they're the x points. So I'll just squeeze that in. X is equal to A and x is equal to B. In other words, the x-axis points in there. Okay. Similarly, if you have something that's rotated around the y-axis, so you've got some function like this. Again, I'm trying to do the green, it's just not happening for me. Something like that, and it's rotated around. If we rotate that around the y-axis between the point A and B, in other words, spin it around that way to create a shape, and that shape would look like pretty bad. Something like that. If we spun that around with your sort of radius like that and that, that's the sort of so that if we did that, the volume would be equal to, and in this case we would need to know x as a function of y. Okay, so again we need to know the inverse of that function. So x as a function of y. Here we had y as a function of x. Here we'd need x as a function of y, and so that would be equal to pi, the integral from y equals a, because we want to know the y values from y equals b, of f of y dy. Oops, fy squared. And so they're the two formula, depending on whether you're working with going around the x-axis or the y-axis. Okay, so that's the y. That's rotated around the y-axis. Okay, let's go straight to some examples and have a bit of a play. So let's just go into it. Let's rotate y. I'll just do some really easy examples because I just want you to see the mechanics. You can do the more difficult ones. You can see those in class. Rotate y around the x-axis. Between x equals -1 and 1. Okay, and find the volume. Okay, so y equals e to the x is something like this. And like that, crosses at 1 there. And what we want is the area between -1 and 1, so this area in here. And what we're going to do is rotate that around the x-axis, so it's going to sort of get spun around the x-axis. That's going to make sort of like a horn shape or something like that. Okay, so let's do this. So the volume will be equal to pi, never forget the pi, it'll ruin you, between -1 and 1. And what we want is the function e of x, that's our function, but we're going to square that function, dx. And there's your volume right there. At this point you could enter it in your calculator, get an answer, and you're finished. Or do it by hand, because you need to know how to do it by hand as well. I'll just rewrite that, -1 to 1, this is e to the 2x dx equals, right, I'll leave the pi at the front and we'll integrate. This is half e to the 2x between 1 and -1 equals pi, and put it in brackets, put the 1 in there, we get half e squared, and then we'll minus half e -2 into there. And basically that's our answer there. It doesn't get much nicer than that. Can we simplify that? Not really. I might just go pi, half pi on 2, bracket e squared minus e to the -2. Doesn't get much nicer than that. There you go. There's the volume, and it's units cubed, like that. You can chuck it in your calculator and find the approximate value for that, but the exact doesn't get much better than that. So there's the volume of that that trumpet, that horn sort of shape. If that's rotated around, your volume will be equal to that. Cool. Let's check out something else. Let's do a rotation around the y-axis. Have a look at that. What if we rotate y equals cos -1x around the y-axis? Let's do the whole lot of it because it's an interesting shape. Between y is equal to -pi on 2 and y is equal to pi on 2. Okay, so cos -1x function is a good one. Oh, that's pretty good. That's not a bad start to the day. Okay, right. So what does this look like? I'll just quickly put, oh, what am I doing? It's not pi on 2 at all. You're probably thinking, what is he doing? -1, and there's -pi on 2 there. And what am I doing? You're probably yelling out over your computers, you're drawing it wrong, you idiots. Okay, so let me start again. Cos -1 looks like this, going up to, and I'm going to change these values up here too. I thought I was going so well. Between 0 and pi. Let's have a look at this, what happens when we rotate this around. So that is pi on 2. That is pi. There's 1, there's -1. Okay, so we want it between y is equal to 0 and y is equal to pi. What will that look like if you rotate that? So if you get that area and that area there, and you sort of, that gets rotated around and that gets rotated around. Now what you end up with is like this hourglass shape, if you can sort of imagine it. Sort of, that gets rotated, that gets rotated, and you sort of get this cool sort of 3D hourglass shape, which is pretty cool. So anyway, let's calculate the volume of this guy. The formula is the volume is equal to pi from A to B. I'll just write the formula down. A to B of f of y squared dy. Okay, because we're rotating around the y-axis. Now, what is our f of y? Well, at the moment we know y is a function of x, and so we need to convert that. So we know y equals cos -1x. We need to rearrange this for x. So therefore, x is equal to cos y. That is our function of y. So therefore, volume is equal to pi between, what are our y values? Between 0 and pi of our function of y, which is cos y, but that is squared dy. Okay, so that's our volume. Should I do this? Tempted just to tell you to put in your calculator because I'm in a hurry, but what that will be equal to is pi to 0. Cos squared, how do you integrate cos squared? Well, we'll convert into half plus a half cos 2y dy. We've used double angle formula, and you'd keep going. I'm not going to keep going, but you'll get, you can integrate that and blah blah blah. So you know, go x over 2, that's supposed to be an integral, x over 2 plus, and when you integrate that, the cos will go to sine, so plus 1/4 sine 2y, etc, etc. Well, I have integrated, so that should be, it was correct. Pi to 0. I feel like I'm going to finish it, but I won't. And then you substitute values in there. So that's how you do that particular rotation. Just want to show you one more thing, that's why I'm in a hurry. I just want to quickly show you what happens when you have two functions. So if you have a function like that and some function like this, what happens when you rotate an area between two curves around the x-axis? Okay, so you can sort of start getting weird sort of shapes that sort of, you know, I'm not a very good drawer, but you can start getting shapes that sort of have tubed and things like that. This would create sort of like a tube sort of shape. So if you've got f of x on the top, g of x down the bottom, then your area volume will be equal to pi, integral from a to b, where that's a and that's b, of the top function squared minus the bottom function squared dx. Okay, so I'll just race through a quick example of that, try to beat the clock. Example here, find the y equals x. I'm going to choose a quick easy one, y equals x squared. Find the volume, find the volume when the area between is rotated around the x-axis. Okay, so we'll just plug it in the formula. These, I know where these two meet, I'll just show you quickly. These meet when x is equal to 0 and x is equal to 1, so there's the area we're talking about there. So a quick sketch of that. Y equals x. Y equals x. Drives me insane. Y equals x and y equals x squared looks like that, and so it meets at 1. And what we want is to know when that area is rotated around the x-axis, what is the volume? So the volume will be equal to pi integral from 0 to 1, that's the area we found out where they intercept, from 0 to 1 of the top function squared. So the top function is y equals x, so it's x squared, minus the bottom function squared, so minus x squared dx. And so there's your integral there. Again, I'm not going to finish it, but it's just a matter of fulfilling this. So x squared will be a third x cubed minus x to the power 4, so minus 1/5 x to the power 5, and valuing that 1 to 0. I'll finish it off because it's the easy numbers. Equals pi, put 1 in, you get 1/3 minus 1/5, and then minus 0 and things like that. And so we get 1/3 minus 1/5, that's 5/15 minus 3/15, that's 2/15 at pi, over 15 units cubed. And so there's your answer for your problem. Thank you, hope that makes sense, and I squeezed it out. Thank you.